Good afternoon, everyone. We will start the oral session 14 of this Congress, where we will present works developed in innovation and development, new products, materials, and fuels based on forestry areas. We will have three presentations. The main focus is to promote the circular economy by reducing and minimizing the use of renewable resources. This session will be done in a row, each with 15 minutes available for the presentation. At the end of presentations, we will have another 15 minutes for questions and answers. Okay? I remind you of the importance to control the time in order to comply with the conference. Okay? Let's go begin with the presentation of Paula Pinto. The name of the project is EUCALYPTUS, the path towards a forest-based bioeconomy. Paula Pinto is a technological research coordinator of XXVI, part of the Navigator company, is in 2016, with responsibility for the technical management of national and European co-funded projects, internal projects, and research and development team. Between 2016 and 2016, researched at the Faculty of Engineering of the University of Porto, University of Aveiro and Reis. That's it?
Yes.
Okay. Cheers.
Thank you very much, Mr. Chairman. Okay, can you listen to me? Okay, now it's ready. The aim of my communication is to present the main results and the impacts of the EUCALYPTUS project as a path towards a forest-based bioeconomy. In fact, we have here, I must say that we have here 9 persons, which were the persons responsible for the technical affairs related with the project. And I have today a big responsibility because I'm represented almost 200 people that works for almost 5 years in this project. So I hope to give you a good overview of all the main outputs and the achievements of this project. So this project, in fact, was the largest investment in Portugal in R&D area in forest-based bioeconomy, in particular with the eucalyptus. The objective was to respond to some challenges on pulp, on paper, and coated-free and tissue, and also in biorefinery. It was promoted by the Navigator company, so of course these three are the main, is the core business of the company, but we are aware, of course, about new opportunities on biorefinery, bioproducts from forest-based biomass, side streams, and also new products from pulp. So I will give you an overview about this. It was about 5 years of hard work. Navigator with Reis and University of Coimbra and University of Aveiro. These entities were the co-promoters of the project, but in fact we have a collaboration of many other entities, 7 with a spin-off of University of Minho. We had as well 2 invited chairs. One of the chairs was with us in Wednesday, but since then I didn't saw him. It was Professor Tad Maloney, with the invited chair from University of Coimbra in paper science, and we had also Professor Falk from Boku University, and finally 1 consultant, Peter Axgaard. So what is the relevance of a project like this? A big opportunity for us, for sure, because in the next years, until 2050, we preview that we have about 50% of increase in value from bioproducts. But we are talking in both bioproducts, new bioproducts from forest, And we are talking as well in pulp and paper products already established. So in the project we have all these areas. We have pulp, we have paper, tissue, the conventional ones, and we have also other bioproducts that we have been exploring. So this graphic is only to show that Portugal is not in a bad position, considering that the roundwood production currently no, because this study came from some years ago. But okay, we have facing this roundwood production, we have a gross value added very sympathetic for the production that we have. We must compare, for example, with Austria, with a similar area, geographical area to Portugal, and with double of production of roundwood, and of course almost double of the gross head value. So Portugal, is to say that Portugal is in a good position for this kind of added value products, but we have also some space to improve, as was encouraged by one of the ministers of Portugal. Yes, we have important role, the forest industry, pulp and paper industry, in sustainable bioeconomy in Portugal. So moving to Impactus project, I have here some general indicators, only to let you know the impact, some indicators that give us a perspective of the impact. For example, we have a huge number of publications and participation on conferences as well. We have contributed as well for the training of new students. We have more than 100 proof of concepts and also dozens of prototypes coming from the Impactus project. And of course patents. The intellectual properties was one of the main outputs. And I'm not saying here the products, because I will talk about this in the next slides. Something strange here. Can you listen to me? It's okay. Okay. So I will show some selected outcomes. This is not very fair, because we have 45 sub-projects within the Impactus project, and this is only an overview of some of them, in particular that ones that give up to products, commercial products. So one of them, it was in fact the development of the process to produce hello? Okay. To produce a new grade of pulp that we call high-yield pulp, which allow us to save wood, about 20% in the specific wood consumption, and we call it ICAP. The ICAP was the raw material for a new grade of paper that was launched in 2021, the G-Craft. I think some of you have know about that. Many other outputs from this, for example, to the optimization of pulping conditions, to maximize the yield when we are pulping mixtures of wood. Yesterday we had a communications about that with Bruno and Professora Graça. I must say, for example, bleaching was a topic with two works in this area in pulp, and we have also new data that allow us for the optimization of industrial pulp production, including water savings, and developing knowledge in ovens based on eucalyptus fibers. So new applications for fibers, and also an environmental performance was also considered here. About circular economy, for example, I must say that we had a research line related with the introduction of flying ashes in new products, in cement products. Moving to pulp, to paper and coated wood-free paper, the highlight goes for the production of microfibrillated cellulose as a new additive for pulp to promote the strength of pulp. And the novelty here was related with the source of microfibrillated cellulose, which was unbleached kraft pulp, and it was introduced successfully to improve the strength of the papers. Many other outputs came from this research line, such as sensors in papers with several functions. So this is the paper functionality to increase the value. And other example is new formulations to improve the printing quality of paper. Other, for example, cationization of cellulose, cationization of starch, and for example, LCA analysis as well. And of course, most of this is endogenized by the navigator company, or we foresee the licensing because there is 10 patents related with this area. Moving to tissue. Tissue is a very special one because we have 3 commercial products coming from this research line. One of them introduced bleached pulp to produce tissue in a certain percentage, and it was a success, this new product. And other research lines are related with additives introduced in tissue to promote some special characteristics that are differentiator factors, such as aroma and detergency. But I must say that much more was done here. For example, a tool, informatic tool, to preview some characteristics of the tissue, properties of the tissue. LCA analysis was one of the scopes as well, and the development of encapsulated materials to functionalize tissue. Okay, so I will move to biorefinery. For biorefinery, I must be very short. We have 4 main areas: bioactives, cellulosic sugars, and these cellulosic sugars goes on to bioethanol and bacterial cellulose, lignin products, we have heard about that this morning, and biocomposites reinforced with cellulosic fibers. Just a brief overview. What is the new about bioactives and extractives from biomass? Is a sequential extraction of different fractions with value, with bioactivity, which is mainly essential oil, hydrolate, and another fraction with a low polarity, about 3 terpenes, and then the phenolics as the last fraction to take value from forest biomass. And we have comproved very important bioactivities, such as, let me say this, because I think all of us think about that, is preventing of Alzheimer's disease and some effect on skin depigmentation. So this is the main outputs from the bioactives. Just another one is the production of xyloligosaccharides as a prebiotic ingredient that we have proven to be effective as prebiotic. So finally, in the bioeconomy, bioproducts and biorefinery, we found value-creating agencies to the core business. This is one of the main scopes of the Impactus project, and we have achieved that. So about the future is to conclude, because I only have one slide. What are we doing with with all these results? Well, we are scaling up. We have recently some infrastructure and equipments to make the scale up of the process. And we launched the co-creation program to call startups to work with us, trying to push forward the new business in partnerships. And finally, we have now the two projects running in the Recovery and Resilience program, and we are pushing as well some of these subjects for a TRL higher with scale up and involving all other industries. Final remarks. I must say that these numbers I already gave you: 5 new products, 8 potential new bioproducts, and two topics that I would like to highlight. That we have promoted highly qualified young researchers with PhD programs and master programs, and we have now an excellent network between university and industry for the new challenge that we have now, that we face in forest-based bioeconomy in Portugal. So, thank you all.
Thank you, Paula. Let's go to the next presentation. The next presentation is by Manuel.
Mas este não, isto é para a câmera direto. Aquele é de...
Manuel is a doctoral student from the Center of Studies for Studies Institute of Romania. She took her bachelor's degree in biology at the Faculdade de Ciências da Universidade de Lisboa and their master degree in biotechnology for sustainable at the ETQB Nova. The project of Manuel is invasive acacia species wood to paper.
So, good afternoon. Thank you for having me. I'm going to present the work entitled Invasive Acacia Species Wood to Paper. It was a work done between Instituto Superior de Agronomia and the Universidade do Beira Interior. It is then in the scope of the project Acacia for Fire PREV, it's missing there, this part, which aims to valorize acacia biomass residues to offset the costs associated with the process to manage the areas that are predominantly dominated by these species. The objective is to reduce the risk of fire and to achieve a greater environmental balance. So acacia species is a genus widely spread as attentional or invasive populations. It is characterized by a rapid growth rate, large accumulation of large amounts of biomass. It has a robust seed banks and the capacity to fix nitrogen. These characteristics make these species to compete with native plants in limited resources such as light, water, and nutrients. The consequences of the presence of these species include decrease in water availability, an increase in the severity and frequency of wildfires, and changes in soil nutrient levels. Here are the pictures of the 5 species that we used in our work, that are 5 of the most predominant species in European Mediterranean countries, being Acacia mianzi, Melanoxylon, Dialbata, Salina, and Longifolia. So the control actions of invasive acacia species generates large amounts of residues that are mostly used for energy production. And the costs of this process hinder their efficiency and upscale. One interesting field of work to use acacia might be pulping industries, in which little is known regarding the potential of using these residues as raw materials. In our work, we studied the potential of these acacia species wood residues to be used as raw materials for bleached crafts, pulping, and paper production. with the objective to, if valorizing these residues, we can implement long-term initiatives to control these species. So our experimental work, we used a response surface methodology to build our experimental design, and we used temperature and active alkali as our variables. We used temperatures between 151 degrees and 179, and active alkali between 16 and 24%. We optimized the conditions of the pulping for each species, and then performed an upscale with those points. Then we made a bleaching step with using a sequence of oxidation with chlorine dioxide and an extraction with sodium hydroxide. So regarding the second part of the work, which was the paper making and characterization, we used Morphy to characterize the morphology of the fibers. And regarding the properties, we analyzed air permeability, tear index, tensile index, brightness and opacity, and Chopra-Reger degree. So the results we obtained with our response surface methodology, the two variables that we analyzed were pulp yields and kappa number. The results we had were between 46% and 58%, with kappa numbers between 6 and 60. We observed that harsh conditions led to lower yield and kappa numbers in our experiments, and the most relevant differences were with the ACACIA salina, in which all points had kappa number lower and kappa number higher, and yields lower than those of the other species. And with the ACACIA melanoxylon, it seems to be easier to delignificate at softer conditions. So after we had these experimental results, we built our theoretical method, in which we were able to obtain the optimum points for each species regarding the temperature and active alkali to be used. In here, we choose the pair of variables that would lead the higher yields, with a kappa number of 17, which is the standard number in the industry. Okay. So these are the results. So after we built that theoretical experimental design, we needed to validate our model, and so we went back to the lab, and we made the reactions in small digesters again, and we obtained results that were comparable with the theoretical ones that we were expecting in both yields and kappa number. The most significant difference was with ACACIA melanoxylon, in which we obtained a lower kappa number than the one that we were expected. Okay. So after this, we validate our model because the values were comparable. So we went to do a scale-up. In this scale-up, we saw that we had higher polysaccharides degradation, higher solubilization, and removal of hexanuric acids, since the yields that we obtained were lower than the ones in the small digesters that I just showed you. The bleaching step led to mass losses of about 4 to 5% and almost elimination of the hexanuric acids. After this, we did all the paper making, and we went to analyze the properties. Here are the results that we obtained with Morphy. So the fibers of acacia belongs to the short category of fibers. Regarding width, Mianzi and Salina are similar to globulus. I forgot to mention that we use globulus as a reference to validate our results and to compare with the most used species in the industry. And ACACIA longifolia was the species with higher width among all. Regarding the coarseness, it was higher for longifolia once again, and ACACIA delbata and Salina had the lowest values comparing with the other species. So the effect of the beating, because we used unbeaten and refined pulps, the fiber length decreased and the fines, and with it both increased with beating. Regarding the physical properties and strain and optical properties of the paper, so we analyzed the Schopper-Higler, and the results we have were the ones expected, more or less. Upon beating, all the pulps obtained a Schopper-Higler above 30. Only the Albata and Longifolia had one above 40. And Mianzi is a species in which the Schopper-Higler is similar to Globulus. Regarding tensile index, the variation was not very much between all species, and the tear index increased with beating for all species. Regarding brightness and opacity, these both characteristics decreased with beating. Here in brightness, the highest decrease was with the Albata, and comparing the variations between the species in unbeaten and beating pulps, the opacity varies less, the decrease. So, concluding our work, we show that the optimized pulps showed slightly higher yields than those obtained for Globulus. Cassia mienzi and melanoxylon have higher end-sheet strength characteristics, and in all Cassia species that we tested, we verified a substantial loss in optical properties upon refining. Overall, most of the species studied here seem adequate enough for pulping and paper end use, either alone or in addition to Globulus pulp production. So, thank you very much for your attention.
Thank you, Maria, for your presentation. Let's continue with the next presentation and the last of this presentations. The next is Joana Curto. Joana is assistant teacher at professor at the University of the Interior, researcher at the Fiber and Tech Union of FCT, Fibros, Materials and Environmental Technologies, chemical engineer with a doctor in paper engineering. Develops several research activity in the area of chemistry, biotechnology and materials engineering. Author of scientific publications and supervisor of doctors and master's theses. The name of project is Engineering of Eucalyptus and Cannabis Biobased Materials for DERMIC applications using 3D simulation.
Okay, thank you very much. Okay, good afternoon. Thank you very much. I think you can hear me, right? My name is Joana Curto. I would like to thank Tecnicelpa for this conference, the industry and the research institutes that collaborate with us, and in my name and the other co-authors. This work is representing several master theses graduating students, two students in PhD enrolling in PhD, currently one student working in a cannabis industry, and another continuing modeling. So I will be here not presenting all the results, but give you the highlights of some of the aspects that we've been researching in engineering, eucalyptus and cannabis bio-based materials for DERMIC applications. These applications are in the field of patches, dermic and transdermic, and also facial masks for cosmetic and therapeutic applications. And the methodology implies using 3D simulation. If we see the project growth of the European cannabis market, and in a circular economy perspective, we can see that the growth of uses for all the parts of the cannabis plant, the seeds that are used in oil, and we had a master thesis using for development of these products. The flowers, where the active molecules THC and CBD are more concentrated, but also the leaves, where we have been working in teas and other applications, and of course the fibers. The fibers have major importance in paper application, textile, composite materials, And this work is inside a more global perspective in our research unit, Fiber Materials and Environmental Technologies, that is the development of cellulose-based biodegradable materials in the scales of micro and nano fibers and using 3D computational simulation. This is the perspective from the use of alternative fibers, cannabis fibers. Okay, this is an example of a graphical abstract with some of the experimental design. We can see here, we can see here the traditional fibers. Eucalyptus globulus is the base for these materials. Some pinus or PCABs, softwood fibers, can be used to reinforcement, and the optimization of the mixing of this fiber. And also here is very important the retention and the controlled delivery of the active molecules. These kind of systems are also named as drug delivery system, because what we want to optimize is this porosity, this retention of the active molecules. So parallelly there is here the study of the kraft pulping for the cannabis fibers. This was done with cannabis sativa, but other species were tested. The bleaching and the optimization studies conclude that we could do it with an alkaline pulping process and peroxide oxide bleaching stages. The active molecules are often joined with another ones. Here in this work it was the tea, the Camellia sinensis, which is a tea from Azores. In this case our student was from Azores, and the company was interested in the conjugation of these molecules because the tea from cannabis has no flavor, and the tea with a tea with Camellia sinensis has a green tea flavor, much more with organoleptic properties that only cannabis. In terms of the characterization, is the common GC-MES characterization. Being one of the questions, the active compound retention. I will speak more about this, and how we have done the computational simulation to optimize these studies. Another design of experiments here. Here we can see that we have another plant, and this has been going for more than 5 years, so there are 2 PhD students enrolled in these studies. And in here we have done a hydrodistillation to obtain the essential oil of cannabis sativa and other plants. We have used extraction to have a sense of the volatile molecules and the chromatography, and parallelly in the second line the optimization of the fiber matrix 3D structure using computational simulation from the fiber model to obtain the porosity, the retention, the incorporation of the active molecules that we wanted to achieve for different applications. Some of the aspects of the fiber simulation, for instance, here we have the definition of the fiber in 3D, and then the fibers are deposited in a structure like we do with paper, and we can change the mixtures. Here in this figure we have cannabis sativa and hardwood fibers in a mixture, so we can change the fibers, the proportions, and we can study 1,000 structures, and then we go to the lab to verify 10 of them. In terms of the retention, one of the questions is the techniques to prove that our tea, our cannabis, THC molecules are retained in our drug delivery system, in our cellulose-based structure. Here in this work we have used the color, because clearly it was a parameter, but also ADCs to see the elements when there is some elements that are distinct to prove this retention. And here are some of the results. Okay, as you can see in the first image, we have studied hardwood fibers, softwood fibers, because they are used as reinforcement in these materials, and the perspective here is to replace some of the softwood fibers by cannabis sativa fibers. The optimized structure that we have obtained is represented here, and we could obtain an optimized structure with eucalyptus, fibers from hemp, and cellulose micro-nanofibrillated, and this was the best combination for porosity, retention, and the properties of this kind of tissue material: softness, absorption, strength. So the methodology is to model the fibers, then model the structure and obtain some parameters with the scanning electron microscopy of the structure, and then using the 3D computational simulation to have a lot more of possibilities, and then do a data treatment to see where the optimums are. Okay. In this cannabis sativa project, some of the fibers were textile dimension fibers, so they are used in a parallel project to textile. So here in the top we have these textile examples, and in the bottom we have a 60 grams per square meter ISO standard sheet that you produce in the lab to control what happens to study. And then we made some adaptation of the ISO stand, no pressing, more grammage, because this will be multi-layer materials, and sometimes there will be a layer that is more tissue, where softness and retention is very important, and other layers where we want to improve, to have another porosity and have other properties. So we can use the computational simulation to have a screening or about 1,000 structures, and then use this to go to the lab and only make 10 validation structures, and we go faster to our goal of obtaining optimized materials. This work, there are here some publications. Okay, let me see. Okay. So we'll find that we were working, this started like 5 years ago, and in parallel the tissue project that Paula explained in Impactus. So to optimize the structures, we have taken in consideration the tissue process, the liquid absorbency properties, the retention of our active molecules depend on this retention, the 3D fiber modeling, and then a tissue simulator that was developed for Impactus project and can be used to optimize the furnish, and then, if explored, to optimize the retention of these molecules. I've put here some of publications, but in tissue paper materials we have more than 20 publications to PhD theses concerning the enzymatic treatment, the micro-nanofibrillated cellulose, and a lot of aspects that I will not refer here, but they are open for reading. Okay, returning to the 3D computational simulation. As you can see, we can have an idea and a quantification of porosity, thickness, fiber distribution, pore distribution, if you have a simulation of our raw materials. And we can, here are some examples. In blue we have eucalyptus, and in blue and pink we have magenta, we have eucalyptus and some reinforcement fibers. So using computational simulation, we could have more data if these softwood fibers would be better to be a refined Pinus or Pythia, or what we needed to do to our cannabis fibers so they will have the flexibility that will help us have strength but maintaining softness properties, and also the porosity. So, okay, this is another example of an experimental design. Here the novelty was the use of an emulsion. Okay, we started, our active molecules were in forms of extract, essential oils, and here we have put our molecules in a water, oil in water and water in oil emulsions, both of them, and we have tested this incorporation and these kinetics to development of this application. Okay, this is about the characterization. Not only we need to do the characterization in our essential oils of the active molecules, but also if they are staying retained in these drug delivery systems, in these tissues that retain and release these molecules. The example here is Formenta pipirita. It's one of the molecules that you use a lot in combination with the others because its menthol is a a friendly molecule for most applications. We can all of us recognize the odor of menthol. As you can see, mentha piperita is the major component, but also menthol, for instance, if you are using the oil instead of the molecule alone, the menthol from synthesis, menthol, which is acetone, will have some relaxing properties. So an essential oil is different from having the molecules in separate. And in these products, bio-based products, we use the approach of having these molecules from all the plant. Okay, an example here also for the menthol. It's a molecule that has an OH group, but cellulose and the additives that we have been using here, that also were ketosane and others, they all have OH groups. So in this kind of analysis, we need to go further and we need to compare spectrums, see the groups that vibrate in FT, of course, but then also the fingerprint to check if the data tell us this is the same sample, another sample, and this is we find this very important in our characterization. Okay, finally, I think my simulation is working, so maybe we will see a structure made with cellulose fibers. We can see fiber by fiber. When they are deposited, it's a plain structure, but the fibers will deposit in top of each other, and if everything goes well with MATLAB, this has been done in MATLAB, we'll see a structure made from cellulose fibers and cannabis fibers, appearing in the right image in the bottom. Okay, so what are we taking in consideration for these fibers? We are taking length, width, but also what happens in the Z direction, flexibility, lumen, void, degree of collapse. This model takes in consideration the fibers in 3D. That's why we can accurately predict many of the process operations like beating, refining, differences that occur in the process that changes these properties, and the insertion of other fibers. So, okay, I think our structure is coming along, okay. When developing application, it's very important to have stable structures with uniform properties. So some of our work is to obtain these in a consistent way to the industries that we work with. Okay, and the porosity is here the key parameter in terms of modeling. Now it's going faster, okay, so we'll see the structure, I hope, appearing soon. How am I? Okay. Okay. So, but I think you get the idea from what happens in a fiber, that is going to be the same way as we make an ISO standard structure in the lab, 60 grams per square meter. Here we control all the parameters, the grammage, the thickness, the porosity, the pore distribution, also the relative bonded area, which is related to strength properties, the number of crossings per fiber in the structure, which is, if we use longer fibers, we'll have more contact points in our structures. That's the mechanism that makes the strength increase. But also what happens in the surface for softness properties, which are very important in these applications for DERMIC, for the use in our facial masks, in our cosmetics, but also as patches. The softness, these properties that are at the surface, they can also be modeled with this kind of simulation. So we'll have a lot more of data that you can treat to find our optims and trade-offs. As we know in paper making and drug delivery systems made from cellulose fibers, it's all about trade-offs. If I'm going to increase strength, I will be reducing softness, porosity, and the retention of water-based or oil-based active molecules. It's key parameters if you are doing this kind of materials. So we can, all of that is included in this kind of modeling based in data from the lab, industrial data, so we'll have more information about the properties and the optimization that we are going to do. So I will go on, this will continue. Okay, just to conclude, that we are in the field of development of structured materials using fibers from the different bioresources. This is related with design of tissue paper materials. These are tissue paper materials that retain therapeutic and medicinal or cosmetic molecules. For this retention, it was very important the use of micro-nanofibrillated cellulose. We could obtain optimums with this additive. This here is used as an additive in percentage that go from 1, 5, it depends on the applications. The simulation is a valuable tool to choose from the furnish of these compositions. And finally, this is a field of natural cellulose-based biodegradable materials that will continue to research. I've selected here some of our research. The first one is exactly a 3D fiber-based strategy for optimization of tissue materials using a combination of liquid absorbency retention methods. This is a book chapter, very recent, and then others in Planta, a medicinal planta, where we have presented these combinations of cannabis sativa with THC and CBD and other plants. And finally, what else? Some application with ketosane and for package. Okay, this kind of methodology with experimental and computational simulation can be applied to package materials. We are already doing it. And if you are interested in these fields, of course, I will recommend for more detail these readings. Okay, I'm just finishing by thanking you for your attention. Thank you.
Thank you. Congratulations for the presentations. It's time to questions. We all want to.
Thank you, Paula, Maria, Joana, very nice presentations. I really enjoyed it. I have a few questions to Maria. So really nice work on vacation, and we see many presentations this conference on vacation. Not surprisingly, we could see even yesterday, close to Lausanne, many of these trees taking space for our eucalyptus. My question is, acacia is already a market pulp in Indonesia, for instance. If you compare how is these properties of these several species you have measured against Acacia mangiu or Acacia carsicarpa?
No, we just tested the 5 for wood. We just tested the 5 acacia species that I just mentioned. We didn't compare with other species. We focus on the most common and dominant in the European Mediterranean countries in which it is a problem. I'm not sure about Indonesia, but maybe it's not an invasive.
No, it's planted.
So it's a planted. So we are looking for the valorization of the residues and not the valorizing the tree.
And it was just a matter about benchmarking the properties. Also on the extractive side and sugar composition, it would be also nice to compare those different species against those benchmarks.
Yeah.
In Indonesia, when they started with acacia, they used to then mix tropical hardwood. They also experienced several issues on shifting from mixed tropical hardwood to acacia, such as the extractives. So it would be really nice to understand those differences.
Thank you.
Question 1.
It's one question for Joana Curto about the simulation of structures. If it's possible to simulate structures of, imagine composite structures of nanocellulose clay particles.
Yes.
Even the morphology.
In composites, okay, but I think I can. Okay. Obrigada. Okay, in composites, the simulation is based first in the matrix, the cellulose matrix, and then the voids that in paper are voids will be filled by other polymers. To nano-microcellulose, it's a change of scale, but in terms of voxels, this model is based in voxels. We don't have a problem in terms of memory or any other capacities, so we can have as much scales as we want, and we have done it until nano and micro scales together.
But you can combine it with a different type of morphology. Imagine a clay combined
Yes,
with
yes.
cellulose.
In terms of voxels, everything is a space, a 3D space, and you can put a fiber that is as a length, a width, inside a void, a lumen. It can be, all these 3 dimensions are modeled separately. So if you use a clay and we know the dimension of the crystal, we'll put this particle in our voxel. The thing is that our minimum particle defines the minimal element that we are considering. But because we don't have computational problems, it's a question of defining our minimum voxel, the dimensions of it. Okay, it's okay.
Any questions more?
Thank you. So I have one question for Dr. Paula C. Based on your experience managing the IUCALYPTUS project, what would you say are the main pitfalls of a big and impactful project like this, of managing a project like this? And what would be your advice or recommendation for companies to capitalize on fundamental research such as this?
I understood the second part of the question, but the first one, if you could repeat.
What are the main pitfalls, the main dangers when
Okay.
you're running a project like this?
Well, how many minutes I have?
5 minutes.
Okay.
5 minutes to finish.
Okay, let me think about that. The dangers, I don't know if it's the right word about that, but the challenge to have the right match between the industrial needs and academic needs, because this was a collaborative project between academy and the industry with a specific objectives, and to get the right match between two types of entities is the main challenge in general, I must say. The second one, more technical, is to have some innovative products from a mature industry, which is pulp and paper industry, from technical point of view. Because on bioproducts and biorefinery, we have lots of new products coming, but we have perspectives for new products because the research is going, and we are always, every day, discovering something. So, from technical point of view, to summarize, is to find new innovative products in a mature industry. From the managing is to get together industry and academy. And my advice is to have a good settle, a good baseline to work, a very collaborative work, and a good discussion with the academic partners and with the industrials for setting up the baseline for a good work together in the years of the project, for sure. Is that, I don't know if I answered, okay.
Any small question for a fast answer or finish in this? No more questions? Okay, finalize that. The program continue at 4:30 p.m. in the next room, forum of CEOs.